Okay, so we are moving into an entirely new and very different exam 2 total grade. Yeah, the test corrections will be in the exam 2 total grade. I'll probably also have kind of just a location for test corrections, being like, these are the points you got back total. But again, that won't affect your grade at all. So I kind of like to be transparent of where all of these points are coming from. But it will eventually go into the exam 2 total grade, which again will be the only thing that's actually affecting your grade. So if you don't do test corrections, maybe you'll have a blank, or maybe you'll even have a 0 there, but just know that's not actually affecting your grade at all. It's just kind of a placeholder, so you're aware of where they are. But good question. So yeah, as I was saying, we are moving into a new chapter. It seems like we're going to be shifting gears a lot, but at the same time, maybe not so much, because we're going to be doing a lot of similar processes. So this chapter is all about exponentials and logarithms. And logarithms terrifies some people, but at the end of the day, I think it terrifies people because maybe we're not very strong with just exponentials. And so make sure that you're locking down this concept of exponentials. What does 2 to the third look like? What does 3 squared look like? Stuff like that. Because if you are comfortable with these, and maybe you don't need to know these immediately and you can find them on the calculator, but if you have some sort of intuition on these, then you'll be much more successful in logarithms than just kind of saying, oh, I'm just going to dive into logarithms. And so I say they seem familiar because we're going to be doing transformations. We're going to be doing domain and range, all stuff that we've seen before. We're just going to be doing it with these new functions, these new exponentials, these new logarithms. But the first section, the stuff we're going to do today, has nothing to do with logarithms. Well, other than, exponentials and logarithms are heavily related. Okay, so for starters, we're going to talk about, like, what does a pattern of an exponential look like? If I give you a set of points, can you say, ooh, that looks a lot like a regular function, or that looks a lot like a line, or that looks a lot like this new function? So these tables, we're trying to identify if something is exponential or linear. If it is exponential or linear, we're going to write an equation. If it's not, we're just going to say neither and kind of call it a day at that point. So for this first table right here, is anyone noticing a pattern?
Going up by 2.
Someone's saying something. My audio might be low.
It's going up by 2.
Let me awkwardly fumble around. Oh. I am muted. When did I get muted? Sorry. If people were saying things earlier, can someone say something now?
It's going up by 2.
Yes. Were there any questions earlier then? Because I obviously wasn't hearing people at that point either. Like, just about, like, non-content things. Okay. Well, if there was, let me know. Yes. Sorry, what's up?
I was saying that I don't believe there were any. You're good.
Okay, cool. Thanks. Yeah. So we notice here in this table that it's increasing by 2 every time. -2 to 0 to 2 to 4 to 6. And it is kind of subtle, but it is worth mentioning that x is also increasing kind of at the same each time. Like, if I had a weird gap of -2 to like 5, 6, 7, then we have to watch for that. But in this case, it's nice. It goes up by 1 every time. So that seems kind of familiar. So what do we call that pattern if we see that?
Linear.
Yeah, it's linear. I believe that was a question on the first exam. Okay, so if it's a question on the first exam, we should be able to also write the equation of this table. Or, yeah, that forms this table. Any thoughts?
Y equals mx plus b.
So we're going to have this, since it is linear, I mean, there are other equations of the line. So if you really like those other equations, you technically could write an equation like that. But we have done a lot of y is equal to mx plus b stuff. So let's kind of stick to that, at least for this example. Okay, so now I need to identify my m and my b.
M is 3.
How are you getting 3?
Because m is your slope, and that's what you're going up by.
And how much are you going up by each time?
Oh, sorry, 2.
Yeah. It also said in the chat, m is equal to 2. And exactly what you were saying, kind of when you were justifying why you think this is linear, it's going up by 2 every single time, or up 2 over 1. So m is 2, great. What's my b?
2.
Yeah, also 2, right? I can look right here. So sometimes we might have to do a little bit of work, that whole plug in a point and then go ahead and solve for b. But here on my table, I have as x is equal to 0, so that's my y-intercept of 2. So then my final answer is 2x plus 2. And bold maybe. Any questions about the first example? Like I said, we've seen this before. It's been a while, but we have seen this before. There isn't really a whole lot of new information on that question. Great. Second table. Is there a pattern? And if so, what is it? Sometimes there's not a pattern. Not always going to see a pattern.
Isn't it multiplying by 2?
Yeah, right. So 1/4 times 1/2 times 1 times 2 times 4. So anytime we are kind of, maybe for the notes here, let's say, if we are adding / subtracting the same in each step. Oh, I don't want that. It's not letting me do. Okay. So if I'm able to find something that I'm adding each time, like in this case there's 2, or subtracting each time, then I will have a linear equation. Anytime I am able to identify something that is multiplying / dividing in each step, and it has to be the same, that's very important, but it's dividing by the same amount in each step, that is going to be our exponential. That is this new term. So this case, we have an exponential. And if you're doing the exam and you want to make sure that you're being extra careful and getting your points, you could justify it in that way. Say, I think it's an exponential because I'm multiplying by 2 in each step. Okay, so we haven't seen an exponential equation before, but if you kind of read the directions of the equation, it's in this form. Y is equal to a times b to the x. Exponentials show up a lot. They're typically seen in stuff that increases very quickly. So animal population growth, especially kind of bunnies, is something that is referenced a lot. Usually has kind of a slow increase. When you have maybe 2, not a whole lot is going to change in a couple of days. But when you have 100, it's going to very much increase a lot faster and increase. So you are going to maybe just like to have something as a reference. Usually we think of an exponential as something that looks like this. And so another thing that is mentioned a lot in the media right now is kind of COVID. And maybe it's not following an exponential growth rate as much anymore, but certainly towards the beginning of the pandemic, it was. It was kind of, oh, okay, we only have 1 or 2 cases in the US. That's not a big deal. Next day, oh, okay, 4 or 5 seems not great, but still not terrible. Fast forward to a month, and now we're talking about cases in the thousands and tens of thousands and stuff like that. Okay, so that is what an exponential looks like. This is typically what the equation breakdown looks like. That's the most generic way to describe an exponential. There are kind of other fancier ways, but for this class, that's kind of what we're going to focus mostly on, is this form, y is equal to ax plus b. So my final answer will look something like this. And just like when we had y is equal to mx plus b, this a and b are very distinct things. Particularly, the a represents, in this case, my y-intercept. So instead of b being the y-intercept, confusingly enough, the a is the y-intercept, specifically the y value of the y-intercept, because it is just a value. And my b, we call that my growth rate, but I think, who was it? I think Louise was the one that was like, it's multiplying by 2 each time. So that's essentially very similar to slope as well. It's whatever I'm multiplying each time or whatever I'm dividing by each time. Okay, so with all of that information, what's my A and what's my B?
Review 1 and 2.
Yep. So my y-intercept right here, 0, 1. So it is indeed 1. And my growth rate is what Louise was talking about. It's increasing by 2 each time. So my final answer is what?
Y equals 1 times, or in parentheses 2,
Mhm.
with the power of x.
2 to the x, yeah. The power of x. I usually say to the, but that means power of x. And that is my final answer. Like I said, this seems like a new concept, but also maybe deep down it does feel familiar to what we were doing before, because at the end of the day, we are looking to find our A and our B, just like we were finding our M and our B over here. One of the things is the y-intercept, which, if is nicely enough, could just sometimes be found from the table. And then the growth rate, instead of just adding or subtracting, it's multiplying and dividing. Okay. And so sometimes we could have a table with that looks kind of weird. Like let's say that I have -2 is associated with 10 and -1 is associated with 50 and 0 is associated with 1/3. This is -10. And so that one, yeah, you could argue that there is a pattern there. And maybe if you're really, really good at mathematics, you would be able to build some sort of weird something to the 4th power polynomial that goes through those points. But I would argue if I came across this table and it looks something like this, I would just say, okay, that I can't really tell you any, it doesn't look like there's any really pattern going on. And if that's the case, we would just say, oh, that's not a linear, that's not exponential. So just neither, call it a day. I don't have to find any equation. Is there a pattern? I don't want this. Is there a pattern in this last table?
There's no pattern.
I'm noticing a pattern.
So every other digit, it's -4.
Yeah, right. So it's -4, 0, -4, 0, -4. It's almost kind of like a light switch, right? You're flipping it up, it's -4, you're flipping it down, it's 0, and you're just going up, down, up, down. So there is a pattern, but, and maybe this is what you're getting at. There's a pattern, but it definitely doesn't follow into either of these categories. I'm not multiplying something the same thing every time. I'm not adding or subtracting the same thing every time. So even though there is a pattern, if we're answering what the question's actually asking for, it's neither of these cases. It's not being added. There's not something being added, which is the same every time. There's not something being multiplied, which is the same every time. So even if you notice a pattern, it has to fall into these two categories here in order for us, at least up to this point in mathematics, in order for us to write an equation. So that's not happening. So I call it neither. Thanks for the free points. There's nothing more needed. If you, again, wanted to be extra careful on the exam, you could say neither because there's nothing multiply, divide every time. There's nothing add or subtract. But honestly, I would give full points for neither. Any questions about this? Okay, I'm gonna pause my share because I think I have a video somewhere. Okay, so now we're gonna get into the graph of an exponential. So just like when we were doing transformations the first time, there are parent functions of exponentials. And sure, I don't necessarily have to have a 2 to the x or 1/2 to the x, but this is typically kind of the standard exponential we go to. It's almost the simplest form of an exponential. So if we're giving you an exponential and we're asking you to do all of these transformations, we're going to probably just give you y equals 2 to the x. And so for y equals 2 to the x, you have key points of 0, 1. If you plug in 0, 2 to the 0 is 1. Anything to the 0 power is 1. Hopefully not a big shocker. If I plug in 1, well, 2 to the first is 2. If I plug in 2, 2 squared is 4. And so really, if this wasn't even 2 to the x, like if this was 3 to the x, it's not too terrible finding the key points with the exact same logic. Okay, 3 to the 0 is 1, so one of my key points would be 0, 1. 3 to the first is 3, so one of my key points would be 3, 1, 3, so on and so forth. But as I mentioned, we probably won't see anything like that on the exam. Maybe something in my math lab, because my math lab is me. And so for these equations in general, I have a horizontal asymptote of y is equal to 0. So what does that mean? That means we can kind of see it on the graph already, but my graph's not going to cross below this. Which kind of makes sense when I was talking about what an exponential means. It kind of represents something that goes quickly. And so if we haven't transformed everything, how do we talk about a negative bunny population? Or how do we talk about a negative COVID case? Like you can have negative 10 COVID cases. That doesn't make really any sense. And so that is a horizontal asymptote that my graph will get really close to on the left side, but it won't end up crossing it. My domain, negative infinity to infinity, because my graph actually goes on forever and ever in both directions. Anyone have an idea of what my range will be? It's kind of hidden right now, even on the slide. So if you look carefully, you could find it. But what's my range going to be?
Is it going to be 0 to infinity?
Yep, right. And the 0 is in parentheses. You can kind of see that again on my graph. It's going to get really close to this asymptote on the left side. It's not going to cross it. And then if we go up, it's going to keep going on forever and forever. Perfect, yep. But that is right here. I will have no x-intercepts unless I've transformed my function. My y-intercept is always going to be whatever my thing here is. So for the 2 to the x case, it's just, wait, that's not right. My y-intercept 0, 1. Oh, that's weird. Yeah, so my y-intercept is going to be 0, 1, regardless of what my exponential is. Again, assuming I haven't transformed it. And then increasing and decreasing, again, something you could probably gather. If my b is greater than 0, oh no, sorry, this is correct. It is a, never mind, ignore me. It's going to be increasing. If it is less than 0, or less than 0 is going to be decreasing, or less than 1. I really don't like that slide. Anyways, the important things are here. I want to know this. I want to know this. And this is kind of helpful, but arguably not too terrible to find. Okay, all that aside, let's go into an actual example. Okay, I want to graph this equation. I'm going to turn off my camera and start drawing. So we saw on that slide that I wasn't really crazy about. My general shape is going to look something like this. This is before any transformations, and that's because my parent function is going to be, in this case, y is equal to 2 to the x. Hopefully not too difficult to see where that came from. I have a 2 here, I have some sort of power here, so that's why my parent function is y is equal to 2 to the x. Okay, what are my key points of y is equal to 2 to the x? Kind of saw that on the previous slide. This is definitely a good thing to have on your note card.
key points are going to be 0, 1, 1, 2, and 2, 4.
Okay. So, well, we've seen transformations before. So, anyone have some one or maybe all of the transformations that are happening to my 2 to the x parent function here?
We'd be going to the right too.
I would say right 1. Because in this case, my inside is what's happening to my power. So in my power, I have x minus 1, so that means I'm going to be shifting right 1.
Would you multiply y by -2?
Negative 1. And if we're feeling particularly fancy, we are reflecting over the x-axis. That's the way to say multiplying by -1. Actually, that should be multiply y by -1. Okay, last transformation.
Up 2.
Now I can see why we're thinking, okay, multiply y by -2, but my parent function is 2 itself. So really what's happening is I'm taking my parent function and multiplying it by that -1. So that's where that multiply y by -1 comes from. Okay, up 2. And now I want to go about doing my transformations. How do I do that? Well, I'll start us. I'm going to write the key points down here.
Would your new x values be 1, 2, 3?
Yeah, how did you get there? Sorry, I was trying to catch up. Yeah, how do you get there?
The first step is right 1.
Yeah, so I'm going to add 1 to all of these. One, 2, 3. Just by adding 1 to each of my x values. Perfect. What do I want to use next? This reddish brownish thing. Okay. Next step.
Multiply your y values by -1.
My points become 1, -1, 2, -2, 4. Last step.
Up 2, so add 2 to your y value.
Okay. So my final points are 1, 1, 2, 0, and 3, -2. Plot my graph. By first plotting my points. I got 1 at 1, 1. I got 1 at 2, 0. I got 1 at 3, -2. Now I have these 3 dots. It might be a little bit difficult to think about, okay, what's the actual shape? Am I going to do something like this? Well, for starters, that doesn't really look quite right, but maybe a possibility. Am I going to do something like that? Which again, maybe looks a little bit more right, but not. Maybe you plotted your points not so great. And so the way I can keep track of this is, well, this is my parent function. I'm going to do transformations, but one specifically is I'm reflecting. So my graph needs to be flipped. So it's going to be something like this. So that's where my graph comes from. Now, if I were to ask you what the horizontal asymptote is, does anyone remember how to find the axis of symmetry? Arguably not the exact same thing at all, but the process is very similar. Does anyone remember how to find the axis of symmetry? Like if I had something like this as an aside. What's the axis of symmetry for that equation?
Wouldn't the axis of symmetry be 1?
Yeah.
H.
Yeah, right. It's H. I don't really have to do any mathematics. I can just look at my equation, say my axis of symmetry is 1. Similar to finding my horizontal asymptote, which also leads me to finding my range, right? My horizontal asymptote is always this thing. And in this case, it's y is equal to that thing. So like I said, yeah, as far as actually helping us graph and as far as the concept goes, axis of symmetry and horizontal asymptotes are entirely different things. But as far as the process of actually finding them goes, they're both, okay, I look at something, I say y is equal to that thing. In this case, y is equal to 2. So with that in mind, maybe I can plot my horizontal if I actually want to. What's the domain and range of my new graph? What's my domain? What's my range of this thing?
So would the domain be negative infinity to infinity?
Yep, this is still a classic case 3 situation, yeah. And this information might be helpful. That's the horizontal asymptote of this graph right here. Guesses are fine too. It's a hard question, so if you throw out a guess and it's completely wrong, at least you were brave enough to throw out a guess.
Is it negative infinity to 2?
Yep. Parentheses. So horizontal asymptote helps me graph, but it also helps me determine my range. So that's a lot of stuff. I'm aware there's a lot of stuff going on. It seems like there's a lot of new information, but really the new pieces of information boil down to this, maybe identifying the parent function and this. We have seen everything else before. We've seen key points. We've seen how to do transformations. We've seen actually doing the transformations to the key points. We've seen plotting. We've seen sketching. It just feels like there's a lot of new information because we just learned about this guy today, but really almost entirely a review on the slide. Any questions about this? Okay. So one more concept before I let you guys loose to practice this, because this is an important concept. It takes time to do it. I don't like it on PowerPoint. Write things. Okay. So I have this equation of a graph here. And if you're given an equation of a graph like this, well, you have to be told what the parent function is. So let's say, I think this parent function is actually y is equal to 3 to the x. And sure, I can tell you that the parent function is y equals 3 to the x for a couple of reasons. I've seen a lot of exponentials, but also I think I stole this from the worksheet that has a parent function 3 to the x. So I wouldn't expect you to be able to look at this and say, oh yeah, that's the parent function. But what I would expect you to do is say, okay, this is kind of weird. I know that usually my y-intercept is 1, but now it's at like this weird fraction thing. So my graph has clearly been transformed. How has it been transformed? Again, not the easiest of questions, so guests are always welcome. Guesses are always welcome. Okay, maybe I'll help you guys by sketching this. So this parent function looks like this, right? Because it has that y-intercept of 0, 1. That's always going to be my y-intercept if I just have an exponential like this.
So shift it to the right.
Yep. So then how would I write this new function?
Three to the x minus 1.
Perfect. Yeah, and so yeah, it's Courtney brought up it's an exponential. John said that it's 3 to the x being shifted to the right 1, and so in my general exponential form, if I have something with b to the x with something blah 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 happening, this is kind of the inside that we're used to talking about. And then if I have something happening down here or maybe something happening in front, these are outsides. So we know if it's an up or down or a flip vertically or a stretch vertically, it's going to be doing something outside of my function. If it's being moved right or left or stretched right or left or flipped right or left, it's going to be something on the inside of my function. Okay, so let's pull up the worksheet. Sorry, any questions about that before I pull up the worksheet, I guess is what I should have done.
I got a question. Okay.
Sure.
How can you tell that it's been shifted right 1 instead of like 0.5 or something like that?
That's a fair point. If this was a question on the exam, it should very much clearly label this point and be like, okay, this guy right here is 0 or 1, 1. It should be a little bit more clear. I think I stole these examples from the textbook. But yeah, you're right. If this was a question on the exam, it should clearly say, okay, that point's 1, 1, or it's 1, 2. We shouldn't leave you guessing and saying, oh, it looks like maybe 2/3 or maybe 1. But fair question. And Courtney asked, is there a parent function guide? In the video there, like if you're just talking generally parent functions, you should go back to kind of the transformation video, the very first one where we were dealing with, okay, x squared and absolute value of x and x to the third, stuff like that. But as far as an example very similar to this, there's an example like this in the video, the 6 point, whatever the first video is, 6.3 maybe. I don't know, I'm bad with section things, but yeah, very good question. Any other questions? The worksheet. So first off is exactly what we did with the tables. I believe one of them's linear, maybe 2 of them are exponential, and one of them is neither. These are the shifts of the graphs that we're doing. I already did 6 for you. I think also maybe one of them doesn't have an equation, just because I don't know why I designed the worksheet like that. But one of the big reasons I actually pulled up the worksheet is we'll talk about e to the x. I don't know, transforming functions is difficult enough. So for these questions, just do y is equal to 2 to the x as the parent function. So make this 2, make this 2, make this 2. No need to introduce another new concept. That's difficult and then make you transform it. If we don't talk about E today, we'll definitely talk about it next class period. But yeah, so change all those to do, make your life easier. And then stop at 11 if you get there. I would recommend kind of doing 1 or 2 from each section, just so you're getting a flavor of each of these concepts. Cool. This way all of your group members aren't here for some reason, so I'm just going to throw you in another group. Okay. Okay, so 2 last quick concepts before I let you loose for the day is this concept of E. And so I mentioned kind of, or you probably noticed on the worksheet, that once you get kind of towards the end of it, I start to ask you, okay, let's say you know what the E graph looks like, go ahead and apply the transformations. And the E graph is very similar to any other exponential, except for when we talk about key points, 0, 1 is still one of them. There's nothing in front of my E. I should write key points for the notes. And then the other one that we usually talk about is 1 comma E, which again shouldn't be too shocking. 1 to the E or E to the first is just E. Sometimes if we're feeling particularly fancy, we could also use the key point 2 comma E squared. I honestly don't really see that showing up on the exam, but it is worth mentioning. And I do this E concept will show up on the exam in some way. Maybe it won't be this transformation of key points, because that's a little bit hard to grasp and a little bit hard to graph, like graphing 2.718. It's not the easiest thing in the world, but it will show up in the term of maybe we're going to be doing an application question. E is great for application questions. Maybe we're going to be doing things with the natural log, which we'll see next time. But that's really popular thing in logarithms. And so the reason why E is so popular is it's a very good way to do that population growth type of thing. So I mentioned at the beginning of this lecture that if we have an exponential, it's great for modeling population growth, is great for modeling growth of a virus or decay of some sort of chemical substance. E is very, very good at population growth. This, for whatever reason, this guy shows up a lot as kind of the base of the exponential. It's also really good for compound continuous interest and stuff like that. If you know anything about interest, like calculating the interest of a loan or something like that, this E shows up that if you are doing that interest of a loan or interest in your bank account, and you're doing it forever and ever and ever and constantly, then E does end up showing up. That's kind of a whole lesson in calculus, but that's where this shows up, and that's why it is so popular. So E is a very famous exponential, and it's also very famous in logarithms, so we see it crop up a lot. But at the end of the day, to remove confusion, when you see E, don't think of it as a variable. This is not a variable. This isn't a Y or a Z or a W or anything like that. When you see this E, it's a very famous number. We use it so often, and it represents 2.718 something, just like pi. Pi is a Greek letter, so you could use it as a variable, but you probably shouldn't, because anytime we think of pi, we think of the famous 3.14159. Very similar. E is very similar to pi in that we use it a lot with applications and stuff like that. So technically we could use it as a variable, but a lot of mathematicians, when they see E, they think of this 2.718 or whatever. Okay, so that's just an introduction to E. I'm not really going to do all these transformations, but if you wanted to, it'd be the exact same transformations. You just would apply them to these points. And then if you were forced to graph, like if MyMathLab's not being particularly nice, if you were forced to graph these, I would just throw it in your calculator and say, okay, what is E squared? Or what is E? Oh, it's 2.718, whatever. Okay. Now, to kind of lead us into the next lesson, and yeah, it kind of sucks for me to throw out concepts to you guys and not give you time to practice it, but we will see stuff like this next class period as well. So yeah, I'm kind of throwing it down and just leaving it out there. We'll have time to practice it next time. But this is where this intuition of understanding what exponentials are and how they work start to come into play. So one of the properties of exponentials is that if I have this, let's say 2 to some power, and that it is equal to 2 to some power on the other side, well, oddly enough, if those two, we call them bases, if those two bases are exactly the same, I can just get rid of them. So my equation quite nicely becomes, well, basic's always a dangerous word in mathematics, but a fairly basic algebra problem. The twos match up, so I don't really care about them. I want to have my powers equal to each other, which kind of makes sense if you think about it, right? If I have 2 to something and 2 to something on the either side, as long as those something powers are the same, 2 taken to that power will also be the same result. So here I'll just kind of quickly run through the algebra. I'd subtract x from both sides, subtract the 2 over, so I would get x is equal to -3, or sorry, 2x is equal to -3. X is equal to -3/2. And one of the nice things about solving exponentials are these are very checkable things. If I wanted to check this answer, we'll just throw it into the power of both of these things. I maybe use my calculator, but at the end of the day, they both should be equal to each other. Any questions about that? Okay. One of the key things I mentioned I kind of glossed over is this trick is awesome. Makes my life pretty easy. I just have to solve basic algebra and not worry about these exponentials anymore. These have to be the same, the bases. So this 2 has to match this 2. If they do not match, they are solvable. It's a little bit more of a headache, but I can't do this cool, neat trick of, oh, cool, the bases are the same, powers equal to each other, do some basic algebra. So I have this question over here. On face value, I can't use that trick. Why can't I use that trick? Well, I have 3 here. I have 3 here. But if I stop and think about it, if I'm fairly good, okay with my powers, I might say, oh, 3 and 9 kind of, they seem heavily related. There's a lot of things I can do to 3 to make it into 9 and vice versa. So power-wise, how are 3 and 9 related? Is there some power that I can take 3 to that'll get me 9 or vice versa?
So 3 squared is 9.
Yeah, right? Yeah, hopefully nothing too shocking there. 3 times 3 is 9. And so what I can say is, okay, these bases don't end up matching up, but, well, what if I say this is 3 squared? And sure, technically, if I want to be careful, it should be 3 squared times x. But if I'm able to do that, so if I'm able to make a slight manipulation of, I want the bases to match up. Oh, okay, 9 is actually 3 squared. Well, I can adjust this to, instead of calling it 9, calling it 3 squared. And then, hooray, I have the 2 bases matching up again. That's great. Now I can just drop out both parts, both bases, and then I'll get x plus 1 is equal to 2x. Honestly, this is a one-step problem. Subtract x from both sides, x is equal to 1. And in this case, checking it is so simple that we can just talk through it. If I plug in 1 for my x here, okay, well then I get 3 to the 1 plus 1, so 3 squared is 9. 9 to the first is 9. My answer works. And so I would recommend, if these two problems seem terrifying to you, maybe just kind of look up or kind of spend a couple of minutes the next few days saying, okay, I'm going to make sure I feel comfortable. What's 2 squared? What's 3 squared? What's 4 squared? What's 2 cubed? What's 3 cubed? I'm not going to ask you something like, okay, tell me what 5 to the 30th is or something like that. But if you are able to kind of quickly see these powers, it's going to make your life a lot easier. Yes, you have a calculator. Yes, within a couple of seconds, you can tell me what 3 squared is or even 8 squared is. But being able to visualize that without a calculator and saying, oh, okay, a C64, what is that? That sounds like a square of something. Oh, right, that's 8 squared. That's going to make logs so much easier for you. Cool. That is it for class today. I think there was something in the chat, so maybe there was a question. Oh, yeah, Austin brought up exactly what we did, so perfect. Cool, so as I mentioned, oh wait, there's now another thing in the chat. I should stop closing it, yeah. As mentioned.
Sorry, I did that early.
Okay, you're good. What was I about to say? I got distracted. Oh yeah, so I'm going to try and have those test corrections graded today. I mentioned last class period that if you wanted to do that kind of bonus inverse question, the y is equal to 3x plus 2 over x minus 1, whatever that is, that's probably not exactly right. If you did do that, I also already put that in your total score. So that should be accounted for. If you honestly want to go back and do that and submit it, just let me know and say, okay, I didn't do the inverse the first time because I was overwhelmed or ran out of time, but I did fix it. I'm fine giving you back those bonus points. And as a reminder, you get 1 point for getting the inverse correct. You get 1 point for doing the domain in range. And then other than that, submit the worksheet for today. I'll have test corrections due graded by the end of the day, and I will see you guys on Wednesday.
Thank you.
Thank
Thank
you.
you.